Okay, so in this problem we have another simple mechanism, and in this case what we have is a link OD, which is rotating clockwise at a constant rate of theta dot, and we're told that when theta dot's equal to some angle, link CA is horizontal. And in this problem what we're asked to do is to take this information, determine the velocity of point A, and also the acceleration of point A at the given value of theta. Okay, so the way I'm going to do this, of course, is to adopt the moving reference frame equations. In this regard, I'm going to need two sets of axes, one fixed and one rotating. And I'm very fortunate in this case that they're already both sketched in for us in this problem, so that should be a relatively straightforward process for us to follow. So in this regard, what I'm going to try to do is I'm going to work my way around this mechanism using velocity first, and then I'll go back and repeat the same using acceleration. So let's do that. So to start, I can say that points A and C lay on the same rigid body, so I can say that the velocity of point A is equal to the velocity of point C, plus in this case the omega of link AC, crossed with the position of A with respect to C. If I go ahead and sketch in what these quantities have to be, I know the velocity of point C is 0, it's a fixed point. Omega AC is going to be some quantity, and in this case I'll say it's in the capital K direction. It could be a positive or negative scalar quantity multiplying that unit vector. And I'll cross that with R of A with respect to C, which in this case I know is a distance L in the capital I. So if I go ahead and expand that out, K cross I is capital J, and so we'll have that the velocity is equal to omega AC times L in the capital J direction. I can then do something similar and say the velocity of point A is also equal to the velocity of point O, and now I need to use a rotating reference frame because A and O are not on the same object, so I'll say plus the velocity of A with respect to O is seen by the observer, plus, in this case, omega of the rotating frame cross R of A with respect to O. So if I do some substitution here, the velocity of point O is 0. The velocity of A with respect to O rel is going to be some value, which I'm going to choose to call, if my quantity here is x, I'm going to call this distance here to b. Let me see how I want to break this down for you. Let's call this v rel, something like that. So I'm going to have v rel in the little I direction. I'm going to add to that to the omega of the rotating frame, which I know is going to be minus theta dot in the little k, because we're rotating clockwise. And I'm going to cross that with R of A with respect to O, which if this distance right here we call d, this is going to be minus d in the little I. Now if we're going to use that, we need to figure out what d is, and in this case I know this length here is of height h, and I essentially want the hypotenuse here to be d, and I know this angle is theta, and so what I can say in this case is the adjacent side over the hypotenuse is a cosine, so I have the cosine at the angle theta is equal to the adjacent over the hypotenuse, which tells me that d, this value that I want to use here, is simply h over the cosine of the angle theta. We know h, we know theta, so we could find d. Okay, so if I go ahead and work out what I have here for the velocity of point A, I have v rel in the I, and then I have k cross I, which gives me a j, so I have plus d times theta dot in the little j. So now if we look carefully, I have two expressions for the velocity of A. I have one right here in terms of the capital J coordinate, and I have two right here in terms of the little I and the little j, so I need to somehow do some projection. And the way I'm going to choose to do that is I'm going to try to rewrite the capital J into terms of the little axes. So in this regard, I'm going to note that the capital J axis is going to equal, well, let's see, if this angle right here is theta, then this angle right here is also going to be theta. So we could say that capital J axis is equal to the cosine of the angle theta in the little I plus the sine of the angle theta in the little j. And once I have that, I can take that and I can plug it back up into here to get a nice result. So now what am I going to have? Well, if I equate the two terms for the velocity of point A, and I look in the little I direction, substituting in the capital J into the original expression, I'll have that omega AC times L times the cosine of the angle theta is going to equal v rel. And if I look in the little j direction, I'm going to have omega AC times L times the sine of the angle theta is equal to d times theta dot. Now if I look at those two equations, what I quickly realize is that I have two equations and two unknowns, and so I can use those to solve for v rel, and also, in this case, the quantity omega AC. course, you can use that VREL to find out the quantities that we want to find in this problem. Namely, we can find the absolute velocity of AC, because we know once we find each of these two quantities and the two equations and two unknowns, we can plug those back in to find the velocity of point A. Okay, now once I've done that, I'll have satisfied the first part of the problem, and so we can move on to the second, which is to try to find the acceleration of point A. And so in this regard, I'm going to adopt a fairly similar procedure. I'm going to start by saying, well, the acceleration of point A has to equal the acceleration of point C plus the angular acceleration of link AC across the position vector of r of A with respect to C, and in this case minus omega squared r of A with respect to C, where this omega, of course, is omega AC. So in this case, we know the acceleration of point C is 0. Alpha AC is an unknown quantity, which will be in plus or minus the capital K direction. We get cross that with r of A with respect to C, which is L in the capital I. I'll subtract from that omega AC quantity squared, a quantity we've already found, times r of A with respect to C, which is L in the capital I. If I go ahead and expand this out here, the first term K cross I will give me capital J, so I'll have alpha AC times L in the capital J, minus omega AC quantity squared times L in the capital I. I can then set that equal to the acceleration of A computed using the point O, which requires, of course, the rotating frame. So I'll have the acceleration of A is equal to the acceleration of O, plus the acceleration of A with respect to O as seen by the observer, plus the angular acceleration of the rotating frame across r of A with respect to O, plus the Coriolis term, which is 2 times omega, across the velocity of A with respect to O as seen by the observer, plus the triple product term, which in this case is omega cross quantity omega cross quantity r of A with respect to O. So we can do some substitution here. The acceleration of point O is going to be 0. Much like I called the velocity of A with respect to O above VREL, here I'm going to call this AREL, and I know that's going to be in the little I direction. I can then add to that alpha cross r of A with respect to O. If we go up to the problem statement, way back here, will tell us that theta dot is rotating at a constant rate, so the angular acceleration of the frame is actually going to be 0. It's nice, we like zeros in these problems. I'm going to add to that 2 omega, so we're going to have 2 times minus theta dot in the little k. I'm going to cross that with v of A with respect to OREL, which is what we called VREL in the little I. Then I'm going to add that to the triple product, which is going to be minus theta dot in the little k, cross with quantity minus theta dot in the little k, cross with r of A with respect to O, which is distance minus d in the little I. So if we go ahead and expand this out here, we're going to have, in this case, AREL in the little I. K cross I is going to give me a J, so I'm going to have minus 2 theta dot times VREL in the little j. And then if I expand this out here, I'm going to have K cross I is going to give me a J. So I'm going to end up here with minus theta dot squared times D in the little j. Pardon me, in the little I. Almost messed that up there. Be careful with that one. Okay, now again, if we look here, we have two expressions for the acceleration of point A. We have one right here, and we have a second right here. In fact, I just realized I did make a mistake. Let me go back here and clean this up. I don't want to make a mistake. If I go ahead and look at this term right here, K cross I is going to give me a J. So I'm actually going to have from here theta dot times D in the little j. And then if I take K cross J, I'm going to get minus an I, so I'm going to actually have minus and minus. This should be a plus. I want to make sure I don't make that mistake. Okay, so anyhow, now we have two expressions for the acceleration of point A. I again need to relate them to one another. Up above, I showed you previously that we'd already established J, capital J, is equal to the cosine of the angle theta in the little I, plus the sine of the angle theta in the little j. And now I also need an expression for, in this case, capital I. So if I go back up here to my drawing, what is capital I? Well, capital I is going to be in this case, so let me just go ahead and look at my angles. If this angle right here is theta, and capital I is up here, then what I'm going to get is if I project this down like so, that actually this angle right here is going to be theta as well. So in this case, if I want to project the theta value, I'm going to have draw a drawing here for us. Here's capital X. Here's little y. Here's little x. Here's big Y. This angle here is theta. And then I continue this through, like so. And then what else can I say? Let's continue this out here, continue this through here, continue this through here. Then I know this angle here is theta. Which means, of course, that this angle right here is also theta. So if I want to project the capital X onto the other two axes, I'm going to have, it's equal to the sine of the angle theta and the little I, minus the cosine of the angle theta and little j. How is that useful? Well, we're going to do a little bit of substitution exercise here. So now if I look at the little I component, from up above there, I'm going to have alpha AC times L times the I component of the j vector, which is the cosine of the angle theta, minus omega AC quantity squared times L times the little I component of the capital I vector, which is the sine of theta, and that's going to equal A rel plus theta dot squared times d. If I look at the j components, I'm going to have, if I go back up here from the first expression, I'm going to have alpha AC times L times the little j component of the capital J, which is the sine of the angle theta. I'm going to have minus omega AC quantity squared times L times the j component of the capital I vector, which is minus the cosine of theta. And that's going to equal minus 2 times theta dot times V rel. And if I stare at those two equations, let me create a little space here before I bleed into the next example. I got enough space here, we'll make it work. We'll simply note that from these two equations, I can solve for alpha AC, and I can also solve for A rel. And if I have those two values, I can take these and I can plug it up here into one of these expressions and get back the acceleration of point A, the thing that we were trying to solve for in the first place. Okay, I think that just about wraps up this problem. From here it's plug and chug. I know you got it. Best of luck.